Today we're going to do a lesson 7 on financial applications. These applications will involve the exponential and logarithmic properties. And we're going to we'll be working with some financial formulas. One of the financial formulas that's very common in a lot of financial areas is the compound interest formula. So we have this formula, A equals P times the quantity 1 plus R over N, and then that's raised to the NT. So what this formula actually calculates, A represents the accumulated value, or what we refer to as the final amount. P is going to represent the present value or initial amount. Sometimes it's referred to as the principal. R is going to represent the annual interest rate. But if you use this formula, it has to be expressed as a decimal. So for instance, 7%, remembers that's 7 per 100. If you divide 7 by 100, that will give you this 0.07. Or you may know the shortcut to change a percent to a decimal. You just move the decimal 2 places to the left. So on a 7, the decimal's on the end. And if you move it 2 places to the left, you would have to add a 0 as a placeholder, and that would give you 0.07. The N is going to be the how many times in a year the amount is compounded or calculated. So when the money is calculated, when the money is compounded, the next balance will be based on this new value. So there's what's called simple interest, and there's what's called compounding interest. By compounding interest, what this does, it helps the money grow a little bit more than simple interest. So in the financial world, if you're compounding, an investment, it's going to grow much quicker the more times it's compounded. The same way if you're taking out a loan, your debt is going to grow much quicker if it's compounded more often. And that's a lot of times with credit cards. They're trying to maximize how much money they can earn from your credit card balance. So a lot of times a credit card balance will be balanced, it'll be compounded daily, which makes it grow rather quickly. And so that's why they kind of tell you don't carry a very high credit card balance, because it can get out of hand in a hurry because of this compounding. So it seems to pick up on this word, this N. So if an investment is compounded semi-annually, this means it's calculated twice a year, so N would equal 2. So semi-annually is going to represent 2. N will equal 2. If we use the word quarterly, that means it's going to be compounded 4 times a year. So in other words, every 3 months would be quarterly. Monthly will represent 12 times. And then daily will be 365 times. Sometimes the banker rule is used, and it's based on 360 days. So depending on our application, we'll have to pay attention, because if it does say use the banker's rule, then we don't use 365 days for daily. We use 360 days for daily. And also time is the time in years for the length of the loan, or the length of the investment. So another formula besides compounding semi-annually, compounding quarterly, compounding monthly, or compounding daily, there's this other formula that's compounding continuously, this formula. So it's represented by A equals P to the RT. So this is where that natural number E comes into play. So sometimes I call this formula PERT. So A equals P times E to the RT. So A again will represent the accumulated value, or the final amount. P is going to represent the present value, or the initial amount. R is the annual. Sometimes you may see the word annum. So that's going to be the annual or yearly interest rate. And remember, it has to be expressed as a decimal when using this formula. And T is going to be the time in years, the length of the loan, or the length of the investment. So like I said, the present value formula, there's another formula that we maybe come across. So sometimes we'll be asked to find the present value. And so you'll be looking at the future value, and you'll multiply that times 1 plus R over N to the negative NT. There's also this present value formula compounded continuously. So this, again, if we're looking for the present value and we know the final value, then we can use this formula P equals A times E to the negative RT. So those are the 4 formulas that we may be coming across in our assignments this time. So some examples of applying these formulas. So this first one says, find the amount that results from each investment. So $100 is invested at 4% compounded quarterly after a period of 2 years. So notice how it says that results. So they're looking for the final amount. So it looks like the formula we're going to be using is going to be A is equal to the principal times 1 plus R over N raised to the NT. So to use this formula, we have to kind of identify what is A, or I'm sorry, we have A, which we don't know. P, let me see if I can put that in a better spot though. That's going to be too close to our formula. All righty. So we're going to put this over here somewhere out of the way. So A, we don't know. The principal is the initial amount, which is actually 100. The other piece we need to know is the R. So notice how it said 4% is our annual interest rate. So it's going to be 0.04. And it's said compounded quarterly. So that quarterly represents our value for N. That represents 4. And then after a period of two years, that's going to be our time. It's going to be 2. So to find our final amount, what we can do is just replace these values into the formula. So 100 goes in for P times then 1 plus 0.04 divided by 4 raised to the NT. So it's going to be 4 times 2. And 4 times 2, we actually could probably write that as 8. That's not too hard to do. So we'll go just clean that up to be an 8. So if we input this into our formula, so let me see if I can make some room here. So we have 100 times then the quantity 1 plus 0.04 divided by the number of times compounded. And if we raise that to 8, notice that then our new investment will be $108, and usually they'll round to the nearest penny. So it looks like $108.29. So our final amount would be then $128. Oh, sorry, $108.29. So our investment in 2 years made about $8.29 in interest. So if we look at this next one, I have $700 invested at 6% compounded daily after a period of 2 years. So again, we're looking for the final amount. $700 is our initial investment, so that's our present value or our principal. So again, the formula is going to be A equals this P times 1 plus R over N to the NT. And it's a good idea to identify what we have the A, which we don't know. The P is our initial investment, or our present value, which is 700. The R is the interest rate, annual interest rate. So that's 0.06. And then it's compounded daily. So I believe the book is using 365 there. I don't think they're using banker's rule. And the length of time is 2 years. So if we insert that into our formula, we have 700 is our principal times 1 plus 0.06 divided by 365 raised to the 2 times 365. So let's see if we can make the calculator do that problem. So we'll clear that off. So 700, and then we have 1 plus 0.06 divided by 365. And then it's going to be raised to the 2 times 365. And if we hit enter, that gives us $789.24. So that would be, notice how the percent really affects growth a little bit too. Also, the amount of money, those are the big 2 factors in earning money off of investments is your initial amount and your interest rate. And then the rest of it is just where it gets really powerful in the growing part. So let's see, 789.24. So that would be, let me put dollar signs up there because these are dollar values. So that would end up being my final amount of my investment. So let's look at another example. We have an investment that's $400 at 7% compounded continuously after a period of 3 years. So since it says compounded continuously, that's the hint of what formula we use. So this is not going to be the other one. This is going to be the PERT formula. So A equals P times E to the RT. So we have now to identify the principal. The initial investment is 400. The rate is going to be the 0.07, and the time will be in 3 years. So if we evaluate this, so we have now 400 times E raised to the 0.07 times 3. So it looks like we got that set up correctly. So if I clear this off here, so 400 times E, E's above that LM button. So I can get to that. Yeah, and then we need a X1 is 0.07 times 3. Come down, close off my parenthesis. It looks pretty good. Since it looks like I didn't really need those parentheses there, but that should work as well. So 493.47 would be our final amount of the investment. So A would equal then $493.47 if I round to the nearest cent. So the next thing is sometimes we'll be looking, find the principal needed to get each amount. In other words, they're looking for the present value. So our goal is to get $75. That's our future value or our final amount after 3 years, and it's compounded 8%. It's 8% compounded quarterly. So that tells me that if we're looking for present value, we're going to be using this formula here. So it looks very similar, except now we use a negative into the T, and the P and the A are switched places there. Let's see if we can put that all together here. So P is going to equal then A times then this 1 plus R over N raised to the negative NT. So now the present value we don't actually know. The future value we do know. The final amount is the 75. The rate of interest is 0.08. And the number of times compounded is quarterly, so that's going to be 4. And the length is 3 years. So we put a 3 there for that. So if we substitute that in, we have now $75 is our final amount. 1 plus 0.08 divided by 4 raised to the negative. N was 4 and T was 3. So I'll just leave that there. We probably could have put a negative 12 there in. It's not that hard to do. So I'll probably do that when I put it into the calculator. So we can clear this off. So looking for the present value. So remember, the present value should be smaller. So 75 times 1 plus this 0.08 divided by 4. Then it's raised to the negative 12. Oop, that's not an exponent though. Back up here. Raised to the negative 12. Make that an exponent. That looks better. So if we enter, we get our present value should have been then, and notice that it is smaller. So we should have, to get that $75 in 3 years, we should have started with, we have to start with an initial investment of $59 and about 14 cents would be that one. So to get $1,500 after 2.5 years, and it's compounded at 1.5% daily. So again, notice how we are looking for our future value. I'm sorry, our present value. So P, we do not know. The A again is the 1,500. The R was 1.5%. So if you're unsure, just type 1.5 divided by 100. But if you move the decimal 2 places to the left, that should be 0.015. And then compounded daily, N would be 365. And the length of it would be 2.5 years, or we call that 2.5 years. So see if we can put that into our formula. So P, we don't know, but it's going to equal then this $1,500 is our final value. 1 plus 0.015. Not a big interest rate, so I don't see a whole lot going on here. Probably have to have a lot of money here. Compound daily is nice, but that's not going to really help us with that 1.5%. So then we have this in negative NT. So I have a negative, and N was 365 times 2.5. So let's see if we can make that happen. We'll go ahead and clean that up. Don't really have to, but so 1,500, and then we have this 1 plus 0.015 divided by 365, and then raised to the negative 365 times 2.5. That looks okay. Hit enter. So notice that, yeah, we had to have a pretty healthy amount as well, because that 1.5% is not really helping us a whole lot. So we had to start with 1,444, so $1,444 and about 79 cents. So it grew a little bit, but not a whole lot. So another thing you may come across is some word problems that are not as clear cut of what you need to be using. And let's see what this one says here. So sometimes you may need to solve the formula. It may need strategies using exponential or logarithmic properties. So let's see what this one does here. So the time required to reach a goal. So it looks like we're looking for a time here. So if Tanisha has $100 to invest, that sounds like an initial amount at 4% per annum. So that sounds annually. It's compound monthly. How long will it be before she has $150? If it's compounded continuously, how long will it be? Okay. So actually, there's like 2 questions here. So the formula sounds like we're compounding, but the catch is we know the initial amount and the final amount. What we're looking for is time. So the formula, it doesn't really matter which one. I'm going to just use the first one because they both have the same things, but this one looks a little bit easier to deal with because it doesn't have a negative exponent. So if A equals P times 1 plus R over N to the NT. So let's see here. So again, the A is going to be the final amount, which was the 150. The P was the initial amount, which is the 100. The rate of interest was 0.04. The number of times compounded, they said monthly, so it's going to be a 12. And the time is going to be, we don't know. That's going to be the unknown. So let's see what we can do with this problem. So we have the 150 for A is going to equal, we know the 100, and we have this 1 plus 0.04 n raised to the nt. So it's going to be actually 12t. So one of the things I can do is go ahead and divide each side by 100 to kind of isolate some things here. So I'm going to divide both sides by 100 to start with to get that out of the way, because I really can't work out the right-hand side because we don't have everything. So I can rewrite this as then, I'm going to bring this over here, give myself some room. So this is going to be 1.5 equals then 1 plus, and again, n we said was 12. So let me clean that up too. We actually knew that was 12. All right, so let's see if I can get this thing to work here. Where'd we go? So n was actually 12 there. So now we have this. So I divide each side by 100. So I have 1 plus 0.04, 1 plus 0.04 divided by 12 raised to the nt. So it's actually 12t. I can also go ahead and clean up. So 12t. So we can go ahead and clean up this 1 plus 0.04 divided by 12. Simplify that a little bit using order of operations. Okay, so that would be that. So we have now 1.5 equals, and we might want to carry this out a few decimal places. So because my lab gets a little picky, so I'll go ahead and carry this out like 4 decimal places. So this is going to be 1.0033 raised to the 12t. So let's see if we can get away with that. Go ahead and changing that. Sometimes we're not allowed to do that. We're not allowed to round to the very end. Now, to solve this, we've learned that if logarithms are involved, then I can bring this exponent down. And what we can do is we can actually take the natural log of each side. So I can take the natural log of 1.5, and that's going to equal then the natural log of, let me see here, I am running out of room. I did not plan this not very well. So I'll do this over here. I'll tell you what, I'm going to go ahead and just erase this up here instead. We don't need this anymore. Okay, make myself a workspace. So let's have now, ln of 1.5 equals the natural log of this 1.0033. It's going to be raised to the 12t. And what we learned is with the law of exponents, that exponent part could be brought down. So this is going to turn into ln of 1.5. ln of 1.5. Okay. And that's going to equal this 12t ln of 1.0033. Now to get t by itself, what I can do is divide both sides by this 12 and this ln of 1.033. So if I divide both sides by that 12 and the natural log of 1.0033, we end up with this statement. So the natural log of 1.5, and that's going to be over 12 times the ln of 1.0033, and that should equal t. So using our calculator, if we clear this off over here, notice how this is kind of a fraction. So I'm going to use that alpha F1 key, alpha F1, to get this fraction stuff here. So the natural log of 1.5 goes on the top. And you could have took the log of both sides too, or whatever log you wanted to, because your calculator is pretty powerful. I'm just so used to the log and the natural log. So then we have this 12, and then we have the natural log of 1.0033. That looks good. So if we enter, we get 10.25 or 10.26 years. So the time would end up being 10.26 years. I'm not sure where my lab wants to round, but that's what we could come up with. So that would be compounding monthly. Okay. Let's go ahead and just do the one that says compounding continuously. So compounding continuously, notice how our formula does change for continuously. So A equals P E to the RT. That's that PERT formula. So we said that final amount was that 150. Looks like I erased it, but there's the 150 was there. The principal was the initial amount. That was that 100. We have this E. Our interest rate was this 4%. So that's going to be 0.04. And since we're compounding continuously, that's where that E came in. We don't have to worry about N anymore. And the duration was, we didn't know. So again, we can divide both sides by 100, and this is going to give me this 1.5 equals E to the 0.04 t. If I take the natural log of both sides, so the natural log of 1.5 equals the natural log of E to the 0.04 t. Remember, the natural log of E to the 0.04 t is just actually just the exponent, because remember, if we have a base and a base, and if we're taking the natural log of E base C, that just means the answer is the exponent. So I can use that property there. So I don't have to deal with that. So the natural log of 1.5 is just equal to 0.04 t. Divide both sides by 0.04. So we end up with the natural log of 1.5 over 0.04. And that does equal my time. So that one actually worked a little better doing continuously, not as much to deal with that E. So let's see if we, again, it looks like a fraction, so I'm going to go ahead and just use that alpha button. Don't have to, really, it's not that complicated, but so the natural log of 1.5, and then we're going to divide that by the 0.04. Hit enter, and we do get, notice that because we're compounding continuously, the time was actually a little bit shorter. So now I'm getting like 10.14 years approximation. Okay. So if we were compounding quarterly, how long would it take? So notice that, 12 months or compound monthly is compounding more often. So it should actually take more time than the 12 months and also the continuously. So let's see what actually happens here. So again, I'm using the same formula where, again, the 150 goes in for the A. The P was the initial amount, which was that 100. And we have this 1 plus R over N. The interest rate was 0.04. Now we're doing quarterly. That's going to be divided by 4. Raised to the NT. So we know the N was 4, but we don't know the time. So again, we kind of did this before. So we can divide both sides by 100. That's going to be 1.5. And we kind of already did, no, that's a little bit different because we did it divided by 12. So we also want to go ahead and evaluate 1 plus this 0.04 divided by 4. So it's going to be 1.01. So we have an exact answer there. So this is going to be 1.01 raised to the 4t. Now remember, to get the log, to get the exponent down on the same line, that's where the logarithm comes in. We can apply the properties of logarithms. So if I take the natural log of each side, natural log of 1.5 equals the natural log of 1.01 to the 4t. This will enable me to bring the 4t down out of the exponent. So this becomes the natural log of 1.5 equals 4 times the natural log of, or 4t times the natural log of 1.01. So now if I divide both sides by the 4 and the natural log of 1.01, that should give me the time. So I'm going to just do that on my calculator. So alpha F1. So the top is going to be that natural log of 1.5. And to get t by itself, the 4 and the natural log of 1.01's got to go away. So I'm going to divide both sides by that. So it's going to be 4 natural log of 1.01. And our answer is supposed to be bigger than 10.26. So let's see what happens here. So we actually got 10.19. Interesting. I don't know if I did anything wrong or not there. I have to kind of look at that one, but I would bet we should have got something different than that. Okay. So 10.19. So I may have to investigate there a little bit more. That doesn't seem, it should take more time, not less time than monthly. So I have to revisit that. So keep that in mind. Something may be suspicious there as far as my rounding goes. Let's see here. Let me double check. I didn't save anything, so let me double check that natural log of let's see here. If I clear that off and evaluate again, 1 plus 0.04 divided by 12. See if I did that wrong or something. 1.0033. Yeah, that looks okay. So let's double check the other part. So alpha F1. So we have the natural log of 1.5. I'm going to divide that by that 12. And then we're going to have the natural log of 1.0033, close, another parenthesis there, hit enter. No, we didn't do anything wrong there, so my thinking must be just a little off there. So anyway, that all looks fine. Okay. Let's look at this one more example here. So how many years will it take an initial investment of $10,000 to grow $25,000? Assume the rate of interest is 6% compounded continuously. So again, this looks like we're using that PERT formula. So A equals P E to the RT. Again, the 25,000 is the final amount. It reached that point. The initial investment was the 10,000. That's going to be our P. E to the RT, so 0.06. And we don't know how long that is, so it's going to be 0.06T. So again, we can divide each side by this 10,000 to kind of clean it up a little bit. So 25,000 divided by 10,000. So we get 2.5, that makes sense. So 2.5 equals E to the 0.06T. Then if we take the natural log of each side, this allows us to get the exponent down where we can solve it using the properties of exponents. So the natural log of 2.5 is equal to then the natural log of E to the 0.06T. So we have the natural log of 2.5 is equal to then, notice that the natural log of E to the 0.06T is just simply 0.06T. So then we can just divide each side by 0.06. So I have the natural log of 2.5 divided by, oops, need a parenthesis there, divided by 0.06. Hit enter. And that gives me a time of about 15.27 years if I'm rounding to the hundredths place. And I'm not sure where my lab's rounding to, so it's approximately 10.27 years would be the time to accumulate that $10,000 investment to make it turn into $25,000. So that's why they kind of say time is money, is when we do stuff like this. So that completes our lesson on 6.7 financial applications.